So hi, and thank you very much for inviting me here, Alexander. So actually I will use a case study to touch up on three topics. So high performance computing, big data. I'm very happy that Marcel touched up on that a bit with the Hadoop data, right? and heavy AI. So for us at Intel, we see AI as an HPC workload. And I grew up from being an HPC consultant into an AI consultant, and I consider myself an AI specialist. Briefly, okay, no. After you read this, So internally, my title is Technical Consulting Engineer. What does that mean? So basically, I talk to the core engineering folks who design the libraries and every software that Intel releases, and the people who uses it. So I'm the link between the end users and the engineers. And I have a background in computer science from Bremen and Munich. I'm currently based in Munich. So with my case study, I will introduce you a problem and how we use AI to solve this problem. And then we'll have a look at the deep learning algorithm that we have designed to solve this problem, and then have a look at the various frameworks involved and how we gain the best performance in order for this neural network to work very nicely. So let's start with some statistics. So why this research that I'm going to present to you, it's actually my little baby project at Intel right now. Why it is so important. First, some numbers. In 2018, there were close to 18 million people who had cancer, and out of this, close to 50%, 9.6 million, led to people dying. So that's quite considerable. And the core of my research is brain tumor finding. So how can you use AI to find brain tumors in people? So the medical term that we use for brain tumors is gliomas, and gliomas are actually the most dangerous types of cancers that you can have. If you have it, it's really bad, and close to 90% of those gliomas, they belong to highly aggressive classes of cancerous tumors. So it's really important to diagnose them, and once you diagnose that you have this, it's crucial to resolve this. And to date, MRI, so magnetic resonance imaging, is the de facto or primary method to screen and diagnose for gliomas. And once you have gone into this MRI machine, we'll create a 3D image of your brain, and then the doctor will have to analyze this. And in order to do that, the doctor will have to segment that 3D volume obtained in that MRI image and analyze all of that slice by slice. And why is segmentation important? For the two ways that you can actually fix the tumor areas. So there are two ways. One is radiography or radiotherapy, where you actually use laser to grill the cancer area, cancer cells, so you can kill them with laser. Or if it's like really, really bad, then you really need to engage a doctor, and then there is surgery to open the brain and then extract the bad cells. So in order to do that, it's important to analyze slice by slice that 3D volumetric MRI scan. And the medical challenge involved in all of this is that first, we actually don't have enough radiologists or medical experts to do that. And also, the segmentation process is very time-consuming and expensive. However, we believe that computers can help, and this is where AI is coming in. And we hope that by pulling in the compute power and the technologies that we have right now in AI, we can hopefully solve this challenge that we have. And on top of that, if you look at this last part, nearly 153 exabytes of healthcare data, so that's in the medical sector. So much data was collected, and that's only in 2013. And I searched endlessly for data for 2018 and 19. I couldn't, but we know that that amount, 153, would reach to over 2,000 by 2020. And now you may ask, what is an exabyte, right? So 1 exabyte is 1 billion gigabytes, or 250 million DVDs worth of information. So that's a lot of data. And 2,000 of these guys, it's a lot. So we have a lot of data, so big data. And it's now time for computers to crunch all this data and give us good results, right? So in my research, I have used an open data set from the MACII challenge. So don't worry about what that means. But anyway, I've got images, labeled data. And my goal was to train a neural network to find cancer. So there are 4 categories, so healthy tissue, or necrosis, or non-enhancing tumor, or an edema, or a loss of enhancing tumor. Okay, forget about these terms, but 4 categories. Essentially, at the end of the day, we want to know whether there is cancer or no cancer, right? And in that 3D model, one element is called a voxel. So the idea is to classify a voxel as being cancer or no cancer. So a voxel in 3D looks like that. So it's like a 3D pixel, kind of. And if you look closely, let me zoom on that guy. You can see like the 4 various areas. So ideally, a neural network will be able to do that for us instead of having a doctor to look at that slice and do that, right? So the result is a summary. That's my summary slide of what I did. The MRI input was what the machine gave us. That's one slice. And then the middle part is what a real doctor, a human, he has looked at that MRI input and he has labeled the cancer areas on that MRI input. And that's what we call the ground truth. I use these two, I feed it into my neural network, I train it so that when a new MRI input comes, a new slice comes, I'm able to predict the cancer region. So that's an example here with an accuracy of 82%. It did quite well, the neural network. There's a white paper on it saying that whenever it's more than 72%, it's already very good. And mine did 82%, not bad. So a little bit of detail on the deep neural network that I use in my algorithm. It's called a UNet. Why UNet? Well, it looks like a U. If you want more information, there's a link down there, so I will not spend too much. But basically, this UNet neural network acts as an autoencoder, so basically encoding in one part and decoding in another part. And this process extracts features from that input image, input slice that we feed into the neural network. And at the end of the day, what we're going to get is cancer or no cancer. From a bird's eye view, my whole algorithm looks like this. We have the input data set, labeled images, so cancer, MRI inputs, and then the labels where there is cancer. We feed it into the neural network. We do the training. That takes some time. And then once the training is done, we have a trained model. Then the job is kind of done. And then we have new patients coming in from the test input, then it goes into the trained model, and then the process of predicting, all the computer science term is inferencing. So we do inferencing, and then we get the results. That's it. So that's what we did. And you may also be curious to know what software we used to make this happen. So that's a summary of the various software used. So of course, the Intel distribution for Python for best performance when it comes to Python. By the way, my whole code, all of it is done in Python. So this is one way to say that with Python you can do a lot of things, and you know that. The deep neural network noise. I use TensorFlow and on top Keras to make life easy. And then Hoverboard is a technology developed by Uber, you know, the car company. You might be surprised why would a car company be involved in AI, but yeah, they developed Hoverboard. Hoverboard is a technology that allows you to split this heavy compute intensive training process onto multiple machines. So this is called distributed training. This is what I do in order to do this training process faster. And then with OpenVINO, I did inferencing faster. So these are the various tools involved. And let's have a look at the numbers I collected. So I hope it's big enough. I try to zoom as much. So when I did this training process on only one machine, 28 cores, Intel Xeon processor, 28 cores with TensorFlow from Google, it took 76 hours to train my whole data set. That's a lot of time. And I was not very pleased with 76 hours, and I thought, okay, what can we do? Of course, use optimized TensorFlow. So this is what Intel has done. Intel has taken TensorFlow from Google, has plugged in a performance mathematical library under it, and then it did much better. And this is represented by the second bar there. I dropped from 76 hours to 43 hours with the Intel optimized TensorFlow on only one machine. And I was still unhappy with 40 plus hours. I said, can I do better? Of course. And the idea is to scale. So then I went from one machine to more machines. So by scaling, with Hoverboard, for instance, that's one before the last, I use 4 machines and 8 workers. So from 1 node to 4 nodes, I dropped from 40 hours to 7.5 hours. And then doubling the number of workers, I further decreased from 7 hours to 505 hours. And the key part here is optimized software. So if you look at the first and the second, it's just a change in software from non-optimized TensorFlow to optimized TensorFlow. Same machine, hardware didn't change. I dropped from 76 hours to 43 hours. That is quite good. And now, of course, plugging all of the software together, including the performance library, the whole software stack looked like this. So on top, I have my work, my end work, my research, and then the software used, TensorFlow, Keras, Hoverboard, OpenVINO. All of this made much more faster with Intel Math Kernel Library, or MKL-DNN. So DNN stands for Deep Neural Network, and that's the highly performant mathematical library that makes this heavy compute involved in AI much faster. And MKL itself, part of it is built in assembly, making all the math-intensive tasks really, really fast. And then scaling on Intel hardware, Intel Xeon Scalable, which we call our big fat processors. They're really beefy. So scaling on these guys help do the training really fast. And now if you're curious to see how this whole thing, the slices, look in a at the end of the day, I will show you this here. This is how it looks like in 3D. So every slice stacked together, and that's how the doctor will see it in this 3D model. So yeah, that's it. If you found this interesting and you would like to play with it, the source code is open. We provide it for free to people. And as we speak, there are 2 research institutes in Germany, one of which is a hospital who have taken this whole source code and adapted it for their real patient data for cancer detection. Thank you. Yes.
First question is?
Yeah. So first of all, do you have a collaboration with the University of Essen there's a professor, there is a professor whose name I forgot. He also started a team project, whatever, in brain tumor detection. If you allow just one sentence to that, the idea was not to reconstruct the whole model and specify areas, but to reduce the amount of contrast media that's used for the patients. So he wanted to reconstruct the contrast of the image instead of using too much contrast media to take orally. And this is a different approach, different problem what he defined. But I wondered if you have collaborations with universities, especially with professors, which is, I think also necessary. Not only to have the technical part, but also the scientific part more involved. So
when you said Hessen, did you mean the Bundesland Hessen or Essen?
Essen.
ESS. Okay. No, I've been working with Uni Mainz, Johannes Gutenberg, so Uni Mainz, not those guys, so I don't know.
Yeah.
But if you know them, you know my name. Just make the link. We are
I should have known the name. I didn't know it come to this, but
okay.
It's great to hear you.
Yeah, cool.
We have time for one last question, and maybe back there.
Okay. Hi, I'm back. Just wondering, are you using the CPUs of Intel, the Platinum versions, right? Is there any chance to get the libraries also running on, the standard version of CPUs of Intel?
Yeah, so our performance libraries are aware of any architecture that you have. So the dispatcher knows, okay, if you have, for instance, a core or, it checks what architecture you have, okay, and it adapts accordingly. And this is how it's able to work as best as possible on any hardware that you have. Any Intel hardware that you have. Yeah. Maybe one, I don't know.
I think he will be around at the big barbecue, and I think you can ask him further questions then. Perfect.
Okay, cool. Thanks, guys.